And then could you please share the link or kind of the address in the what is the chatting
Yes,
window?
yes, I did.
So all students can access the YouTube address, and then if they want to see, I'm not sure it is helpful or not, but anyways, if we some students want to see it, they can access and then, yeah, okay. We are going to study we are going to move on to elasticity. So this is a kind of the atom interactions. Okay, what atom interactions? So there is a kinds of the two main components. One is the repulsions, and another one is attractions. So if there is a power, if there is a power, there is a lot of the room separation distance between atoms. What is there is an attraction force or attraction energy might be dominated, and but at a certain ranges, the repulsion force or repulsion energy could be increased, and then they can make it kind of equilibrium, make it a kind of the equilibrium state, like this one. So if you can see energy is a minimum, we can say this is an equilibrium state. But if we apply the force, the atom distance could be increased like that. Could be increased like this way. At the time, they want to go back to the most stable distance. This it can generate the kind of elastic properties. Okay, uh, so elastic behavior should depend on the magnitude of the internal atomic force. So just imagine if they want to go back to what is if we make it the distance, increase the distance between atoms, they really want to go back stable area, right? Go back. But if the magnitude of the force or energy is stolen, the elastic property is it can depend on the elastic behavior. So, but so it's a lot of the what is the microstructure can affect the elastic properties, but what is if there is a kind of the polycrystalline structures, uh, it could be average, make it average. So elastic properties could be might be we can say in cannot affected by the microstructures. But if we focus on the single crystals, it can affect the elastic behavior significantly. So there's a lot of bonding between atoms. I think you already know about the covalent bonding, metallic bonding, and ionic bondings. It can, in these bondings, electrons could be shared. But is so because of the electron effect, what is there the lots of the interatomic force could be determined. So we just assume there is the sodium ions and chlorine ions. So the sodium and chlorine can make it an NaCl salt. So let me increase the so, but if you already know there is a positive charge and negative charge, and because of the charge difference, they can make it a very strong attraction force or attraction energies. Because of that, interatomic force, the attractive interatomic force could be dominated. So it could be this, but could be this, but it could be what is the depends on the distance. If they have the very long particle distance, interatomic distance, this attraction force could be uh, decreased, reduced. Or if they have a very short interatomic distance, there's interatomic force could be increased. It is very simple, right? So, so there is a distance term, and this is material term. So material term and distance term can affect the attraction force or attraction energies. However, if there is the overlapping between the electron areas, they try to push away because they want to have their own areas. And then if they should, if there is a kind of overlapping, they don't want to share their space. So they try to push away. It can make it a repulsion force, which like this one. So, so the total energy is determined by the attraction energy and repulsion energies. It is related to the material factor A and B, and this is a distance factor. Distance factor is related to the power M and power N, but it is different. So let me show. Um, yeah, okay. I think we can discuss it later, but yeah, okay. Mm, oh, in this case, in case of the Reynolds zones potentials, the M is 6 and N is 12, I think. So, mm, if we use the Reynolds potentials, this is 12 and this is 6. 6 and 12. So you can size the interparticle interatomic potentials or interatomic force. And then, yeah, let me explain this one. So this point is related to the most stable areas, most stable positions, not areas, distance. This is distance. So it is related to zero, potential is 0. So we can easily calculate the force from the potentials. Then we can decide which distance can have the most stable potentials. And but the bond stiffness is decided by the derivative of the force. So this the slope, what is the slope of the force is related to the stiffness. This slope or slope and this one can affect the stiffness. Do you understand? Stiffness is related how strong uh, uh, it's hard to say, but then this is derivative of the force, so we can Like that. So the stiffness could be related to the deceleration. What is the deceleration, the definition of this one? But let's see. But R0 is one is the most stable interatomic distance. But if we apply the force, the distance between the particles is linearly increased. But they want to, but uh, but they want they, but it is kind of the linearly. So it means stiffness is constant at small distance. If you can see, you cannot see any other sort of changes in this area, right? It means one is almost linear relations. So yeah, and then the force, if we apply the force and if there is a lot of bond, it can calculate the force by the integration of the stiffness. So initially, when I explained the stress and strain, I showed the kinds of this case and this case. Do you remember? If we use if there is the two things, we can have more force or more force to make the same increment of the distance between them. So at the time, we need to multiply how many bonds here, and then we can calculate the force. So just imagine if there is an M bond in the crystal structures, and so the applied force is calculated by the force over A. This is the definition of this stress. And then we can calculate the force based on this equation. And then to calculate the areas, we can calculate RR, the one's the interatomic distance between this one and this one is R0, so we can go to the R0 scale. Can you understand? And then if there is the number of N, it could be increased, so and we can calculate it, we can plot these equations. Okay, we can go to the strain explanations. This is the definition of the strain, and then we can solve or we can make the relation between the stress and strain based on the micro point of view. And then we have these relations in the previous slide. Then we introduced the strain. So this part is the exact strain. So we can express the stress strain relation by like that. Can you understand?
I have a question.
Mm-hmm.
Based on the previous slide, it seems like the stress is the average of the summation of the unit crystal.
Mm-hmm.
So I mean because the force is derived from the length of each particles. So the n is the bound of the particles, or is for the crystal unit?
We assume that's the good question. In this derived equation, we just assume the n is what is n is in fact the definition of the n is a bond, but in this equation when we derive the distribution, we can say just the n is a crystal lattice. So at the time we can make it the area is n square, and then there is the n bonding. So it's this is equation. In
Okay.
fact, the definition of the N is the number of bond, the number of bond. But in this when we derive the these relations, we assume this is the one bond.
Okay.
Because let me explain this one. I think this is much better. Um, see. Just focus on this particle, this one, right? So just focus on this one. And then if we uh, use the multiple resurrectors like that, there is if we assume there is a one particles, right? And then these particles as well, there is eight crystals, eight unicells, right? So if we can if we just focus on the one unit cells, this one could be one over eight, or has a one over eight, right? You understand? So if we just focus on this one, there is a full bonding. But if we consider the other crystal structures, this bonding could be shared with the next what is the adjacent neighboring crystal structures, crystal unisters. Because of that, we can say this is N, this is N.
Okay.
Yeah, I think that this is more easy to, this is easy, but if, yeah, do you, yeah, okay. Are you okay?
Yeah, I understand.
Mhm. So we can derive the equations, this one, and then based on the Hooke's law, this one is related to this part. But now we can say is what is modulus is expressed by S0 over R0, and then it is related to interatomic energies, interatomic force. Do you understand? So it means if interatomic force or interatomic energy is very strong, there's bonding energy is very strong. So if we just assume our ionic bonding has the very high bonding energies compared to the van der Waals or hydrazine. Because of that, they had a very high melting point. Kinds of, in case of the magnesium oxide, has a 2,800 degrees C. But if we just consider the argon gas or chlorine gas, has a minus 89 degrees C because they only had a van der Waals interaction. They didn't share the electrons each other. So it is quietly correlated with the Young's modulus data. So if you see the polymers, polymer has a very low melting point compared to the metals or ceramic materials. So they have the very low Young's modulus. But if we focus on the metal ceramic, or ceramic has a very strong interatomic force. Because of that, they have the very high melting point, and then they have the very strong Young's modulus. Do you understand? So metallic bonding and covalent bonding or ionic bonding can affect the Young's modulus significantly because of their interatomic force. So this is a list of the this is the kind of the list of the Young's modulus according to the metal type, polymer type, ceramic type, and composite type. Because of the compound, if we use the composite materials, we can increase or improve the Young's modulus. So just think about just Hooke's law, and then the slope is elastic modulus. We already studied it before, but what is the we are going to study the isotropic solid and or anisotropic solid. What is the crystal structures could be different, depends on their unique crystal structures. You already know. So we are going to have the isotropic solid or anisotropic solid properties. It means isotropic solid is the more properties than what is all properties. The elastic modulus properties is exactly the same in all directions. If we have the kind of the XX, or YY, or ZZ, or XY, and not this direction. So we want to say this one in this square, this space, this space, this space has the same properties, but anisotropic solid has a different what is the different properties according to the phase. So if we consider this phase, if we apply the dispersion force, they have the different elastic modulus by this direction and this direction elastic modulus is very different. So in fact, I missed it. I already explained it before when I saw the examples, but to explain the difference between the anisotropic properties, the Poisson ratio is developed. So if we apply the YY direction or XX directions, it is related to the related to we can explain, we can predict it or calculate the strain based on the Poisson ratios. I think it's already explained before, so I'd like to, I'd like to skip it. So this is Poisson ratios. So based on these simulations, the stress XX and stress strain X direction is related to sigma XX over the elastic modulus, and strain Y is described by the like that. We use the Poisson ratios, and then we can expect the Y direction strain based on if you apply the X directions stress. G direction strain is also calculated by the X directions stress using the Poisson ratios. Then, if we apply the Y direction stress, we can calculate the stress XX strain by these relations. Then y we can easily obtain the y direct or y strains, and GG strain is also less like that. So the G direction strain in case of the G direction case is also the same, the stimulus. And we can calculate the x6 direction, x6 strain, y strain, and GG strain like these relations. So to simplify we can use this. There is kinds of the volumetric changes, volumetric bulk modulus. So at the time we focus on the volume changes. So if we apply the kind of the pressures, we focus on the volume changes. So this is the definition of the bulk modulus, volumetric elastic modulus. Volumetric elastic modulus. So max P is hydrostatic pressures, and then stress M is the mean of the stress x direction, stress y direction, stress dz direction. Then, while the delta is delta is a volume changes. So if we consider the strain, we can easily calculate the volume changes using these relations. P is a compressibilities. The piece of compressibility. So this is the definition of the volumetric elastic modulus. So use these relations, we can make it we can relate the elastic constant. So we can get these relations previously, and then if we make it some of the x strain, y strain, and z strain, we can easily kind of obtain this one, and we can define this one is is a volume change direct tension. Then we can calculate it. We can calculate the volumetric elastic modulus. So we have the relations for the stress elastic stress strain relations of the isotropic solid. So we have these relations. If you can see this table, we can calculate the elastics or shears or bulk, the volumetric modulus, and yeah, this calculate look at the relations. Okay. Do you have any questions? Can I move on to strain energies? Okay. So if we apply the force, the materials could be different. And then based on the definition of the energy and force, we can say this area is related to the energies. This area is related to the energies. So strain energy is directly, strain energy is directly related to the kinds of the make the relation, the deformation when we apply the force. So if we know the deformation of materials, we can calculate it. We can calculate the energy based on this graph. So I think you already know that these relations EU equal to W equal TdS minus PdV. I think you already know the thermodynamic equations, right? Uh, you already know that this one, right? And then Q is related to heat and W is the mechanical work we applied. So, but we didn't think about the heat because there is no we can the generated heat it could be legalizable when we make it when are materials are different. So we can disregard the heat terms and then we just focus on the mechanical work form. So we can calculate we can calculate the energies from these relations. This one, so we can the force and deformations, and force and deformations. Then this one could be derived like this one. The upright force, the load is calculated by the stress uh, multiplied by the areas. And deformation could be expressed by the strength. So the strain, x directions, just focus on the x directions and on dx. So we derive the these relations 1/2 stress, strain, and areas dx. So total elastic energies. This is the total elastic energies. Then, so so if we focus on the energy density and the strain energy density, we can what is we can calculate the strain energy density by the energy du over a dx. Then we can calculate this relation. Can you understand? Okay, so based on the Hooke's rule, if we make it tensions, kinds of tensions, distributions, we can drive the energy density like these relations. But if there is the shears, no tensions, the strain energy could be expressed by these relations. Can you understand? So if we consider the three-dimensional, the expression of the elastic strain energies could be expressed by like this. So sigma xx, strain xx, stress, strain, stress strain, and shear stress and shear strain, shear stress and shear strain. So, but as you can see, this term is quite large, so many people try to introduce the tensor matrix. So, just to use the tensor notations, we can use the kinds of the IJ, epsilon IJ, or IJ, and you know, but yeah. Um, okay, and then elastic strings, or what is we can what is we can explain the Poisson effect based on this equation. So with so we use our Poisson equations. We can calculate. We can express the we can derive the distributions from here. Okay, and then what is the string component can produce the what is the we can derivative the energies, string energies by the differentiate the energies by kind of string components. So at that time, we can drive these relations. Then, is what is the derivative differentiated string energy is what is the produced strain, it can be calculated, can be expressed by like that. So energy, stress, the energy over stress is related to the strain, and energy over strain is related to the stress. Do you understand? So the reason why we consider this one is what is the we can try to explain the anisotropic elastic properties. So as you can see, this one has the, if we focus on the BCC structures, this is the BCC structures. This, the, this one, the arrow highlighted, the red highlight particles could be touched together. So there's interparticle distance is shorter than this one. Or shorter than this one. So this distance is shorter than this one, other longer than this one. So why is it? Because of the difference between the interatomic distance, what is the force or elastic properties could be changed. So so we can say, so to explain this one, we use the kinds of the two terms. It's very similar. The stiffness and one is compliance. So we why to simplify the relation of the energies and energy, stress, and stress like that. So we can introduce the stiffness and compliance based on the Hooke's rule. And then if stiffness is expressed like that, and compliance is expressed as. To simplify the tensor, we use stress Ij and strain KL. At the time, stiffness would be expressed by IJKL. And this is also IJKL. Do you understand? But what is if we sure this lecture quickly and just to imagine this part, just imagine this part. So this is the three component, right? There is a three component. Three component is related to the three what is the strength. So if we apply the sigma xx, they can make it three strengths component. So it is related to the three. It's not just make it three, right? Like that. And then they will make it three componented here, three componented here. Can you understand? So we just focus on this phase, and then if we focus on the sigma, the normal stress, sigma xx, and then sigma xx normal stress can produce the strain by the strain xx, strain xy, strain xd. It can make it shear stress also can make it xx, xy, and xg strain. They can make it also xx, xy, and xg's. So they have the component is 81 component. So oh, I think I missed, there is some missing pages, I think. Uh-huh. Do you have the another pages between them? You don't have it? Oh, yes, this one. So there is a kind of the 81 uh, component, 81 terms. So there's a nine stress tensor, nine strain tensors. It is the nine stress tensor and nine strain tensor could be correlate using the 81, but it's elastic stiffness. This one. So I don't know why it is missing. Well, we can reduce the distance from 81 to 36. 81 to 36. It is could be expressed by like that. We can say normal stress Ij, normal stress Ji is same. Then strain KL, strain LK is same. So, what is the stiffness? IJKL is equal to the stiffness JIKL, and IJKL is equal to JIKL. So we can reduce the 81 term to 6 term. We can simplify that. Can you understand? Then I would like to summarize the stiffness matrix and compliance matrix. So stiffness matrix could be expressed by like that, and compliance matrix could be expressed like this. And then it is making a correlation between stress, strain, work strain, stress. It's complicated, very complicated. So because of the very complicated situation, so many people try to reduce the number, and if we write down x-axis, y, everything, it may take quite a long time. So they make it kinds of the rules. So this is a 1, 1, 2, 2, 3, 3, 2, 3, 1, 3, 1, 2. It is related to the 1, 2, 3, 4, 5, 6. So we can say this is if we just assume this is the this is P, this is Q, P is less low, Q is less column. So just simplified 1, 2, 3. 1, 2, 3 is related to normal stress and strain, and 4, 6, 4, 5, 6 is related to shear strain and shear strain. 1, 2, 3 is related to normal stress, and 4, 5, 6 is related to the shear stress and shear strains. So if we use focus on this part, it is a shear stress and shear strain. So it is simplified to the 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 2, 1, 3, 2, 2, 3. And then this is the normal stress and shear strain. It is related XX, YZ is 1, 4, 1, 5, 1, 6, 2, 4, 2, 5, 2, 6, 3, 4, 3, 5, 3, 6. And just shear stress and normal strain is described like that. And then what is the shear stress and shear strain could be expressed like this, like that. So I mark normal stress term is blue, and shear what is a shear stress and shear strain term is red. Can you understand? Okay. So we can reduce the tensor or rotations then we can simplify the is simplify the relation between the shear stress and shear strain like this, like that. Okay. Then this matrix has this, if we have the same diagonal, what is the diagonal symmetries, we can reduce this term. We can reduce these terms. So we only use these component of the stiffness or compliance. So we try to reduce the component of the matrix based on the symmetries or and the relations of the definition or relation with the shear stress and shear strain. Okay, do you understand? Okay. In fact, when I talk with Professor Winholm and Winholz, he didn't suggest I introduce the tensor in this class because tensor is very complicated and then it can make lots of the confusion. Also, if we make it, if we ask the tensor problem in the exams, I think that he think it can make a lot of problem because of the notations. Notation is very complicated. So if someone make the mistake like that, they couldn't get point. So he didn't recommend the tensors. But in my experience, when I came to the US, I don't know the tensors, so it's really, really difficult when I when I talk with the viscoelastics guys or some minds of mechanical properties guys. They always use the tensors, so it's really, really difficult for me to follow what they said or what they explained. So I don't push them. Push you. I don't push you. You should memorize or you should understand all locations. But just to think about what is a tensor. So to make it, the most important thing is to make relations, to explain the stress and strain relations. They're gonna make it the component. So if we apply the normal stress xx, normal stress xx can produce the xg the xx strain and the xy strain and xg strength. To make it a relation of that, we can we can use a tensor, and then what is each stress or shear stress or normal stress can have the three components because we use the Cartesian coordinate. So three component. So we make it segregated, decompose the force and decompose the strains using the stiffness matrix or compliance matrix. I would like to, even though I would like, but is any of the senior faculties didn't recommend the tensors, just to study what tensor can describe. And then I would like to check your background first. because tensor could be reduced by the symmetry of the crystal structures or material structures. But I would like to check your background first. Do you know are you familiar with the mirror index or the symmetries of the crystals? Have you ever heard about mirror index?
I have before.
Mirror index, and because it's not a prerequisite course, so I would like to check because there is a lot of the polymer guys in this class. So I wonder, are you guys familiar with this one or not? So if you are not familiar with the symmetries or mirror index, I will record this part, and then I will share the link with you, and then I will use this this recording file as a maker class. Or if you are familiar with that, I will think about another maker class. What to think about? Are you guys familiar with the symmetry of the crystals?
No, I think I don't know. I don't really familiar with the symmetry of the
You don't know the
crystal.
symmetries, right?
Yeah.
Okay. So let me make it a recording file for the crystal symmetries. So then, so you don't know about this one, right? The symmetries. So like this one. You are not familiar with it, right?
Yeah.
Okay. Okay, I will make it kinds of the recording files to explain the mirror index and crystal symmetries. Then, based on that, we can reduce these tensors. So we can reduce the tensor, or we can easily just simplify the tensors and calculate the tensors according to the crystal structures, and we can calculate it. Calculate the shear stress or shear strength easily. So I will make it. I will upload the kinds of the explanation of the mirror index and symmetries, crystal symmetries. Okay. But so I will skip next Tuesday. I will skip these sections, and then you can catch up these sections by the recording parts. But I will start next section from here. Here. Mhm. Okay. I'm sorry for late, and then thank you for coming to today's class. And then please send your topic until 11:59. But you don't need. This is not required. If I have not uh, get an email from you, I will send the reference paper tonight. But the most important thing is if you have not received the email from me until tomorrow morning, please remind me. Please remind me. So I will send the papers tonight. But if you don't get the papers until tomorrow morning, this is it means I made a mistake. I make a mistake. So please remind me, email me and send the paper me, blah, 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 blah. So I will, so you can prepare your exam one. Okay, thank you. And then if you have a question or if you want to meet me by the office hours, just email me. But please remind me every day because uh, sometimes I missed your emails. So please remind me every day. Okay. Thank you.
Hey, Dr. Lee, I actually had a question.
Mhm.
Actually, yeah, I did email you, I think last week about the homework one. I just was kind of confused on it. Do you want me to just write a summary over the lectures that you covered for that week and then email it to you?
Mm-hmm. Email to me.
Okay.
Just email to me. Yeah, I sometimes I miss your emails. So just email me whenever. Just if you email me every hours, I'm okay. So just email me.
Okay. Yeah, I forgot I emailed you and I remembered I never heard back. So
Don't
I'll get
hesitate.
that sent.
Mhm.
All right. Thank you.
Thank you. Thanks a lot. Have a good day.
You too. Thanks.